Hello, I'm Eugene Rowe from Timisoara, Romania. I have no partner to discuss some interesting things as one being with the title Darwinian Way not sufficient for apparent intelligent design of life. And I say for abiogenesis, the Darwin way to explain life, random combinations, and natural selection, in my opinion, isn't enough to explain earliest phases of life appearances, age, first cells, DNA, etc. Hard to explain because astounding quantity of information and lot of data processing was needed. So no way, because by random the numbers and the time required are excessively large. It concerned me which other factors than dissipative, strong and balanced open thermodynamic systems could contribute to increase in a significant measure the chances to appear that complex life's components as proteins and DNA in order to explain the apparent intelligent design. What else could be involved? I'm asking Gemini, in- intelligent assistant, and Gemini responding me. Uh, his concern touches upon one of the most significant challenges in the study of biogenesis, the origin of life from non-living matter, explaining the rapid appearance of complex information-rich molecules like proteins and DNA. The consensus is that a purely random combination, a natural selection model, particularly in the very earliest phase before true replication, is insufficient due to the immense improbability of spontaneously assembling a functional self-replicating system. The intelligent design appearance can be addressed by considering mechanisms that bias the chemical reactions toward useful complexity, thereby significantly reducing the effective random search space. Here are factors beyond general dissipative systems that are hypothesized to significantly increase the probability of complex life components appearing effectively, acting as scaffolds and filters for early chemical evolution. 1. Environmental structuring and concentration mechanisms. These factors provide non-random environments that concentrate precursors molecules and promote polymerization, forming long chains like DNA and proteins, which is thermodynamically challenging in a dilute primordial soup. Mineral surfaces, catalysis and protection, clays, iron sulfides, and silica. Many theories suggest that mineral surfaces common and early Earth, such as a deep sea hydrothermal vents, or near volcanic hot springs, acting as catalytic surfaces and scaffolds. They can concentrate organic molecules from dilute solutions and orient them in ways that favor specific non-random reactions like linking amino acids or nucleotides. Wet dry cycles (self-organization). Repeated cycles of hydration and dehydration, e.g. on volcanic coasts or in drying puddles, are now thought to be crucial. Drying concentrates molecules and provides the energy for polymerization. Water must be removed to join monomers. Rewetting allows for the dispersal and testing of the new, longer polymers. Research shows these cycles help molecules self-organize and evolve predictably rather than chaotically. Compartmentalization, forming boundaries like lipid vesicles or protocells (operates coacervates), concentrates reactants, protects delicate new molecules, and allows a localized environment to maintain chemical states different from the surroundings. This is a prerequisite for any form of localized selection or proto-metabolism. 2. Chemical and thermodynamic non-randomness. This addresses the astounding quantity of information challenge by suggesting that chemical properties themselves steer the system towards life's components, making the outcome far from purely random. Thermodynamic selection (bracket) beyond simple dissipation. While life as a whole is a dissipative system (bracket) increasing global entropy by dissipating energy, specific theories propose a thermodynamic selection principle. Systems that can persist and maintain their structure by efficiently dissipating energy (e.g. absorbing and re-radiating UV light) are selected for their stability and longevity even before heredity begins. This is sometimes called dissipative structuring. Autocatalysis and nonlinear reaction networks. A key step is a shift from random chemistry to autocatalytic cycles when a product of a reaction also acts as a catalyst for its own production. This creates positive feedback loops, allowing certain molecular systems to grow exponentially, outcompeting others. outcompeting others. This is a form of chemical self-selection that mimics natural selection without the need for a genetic code, yet the metabolism first hypothesis, like the iron sulfur world theory, focus on the priority of these chemical cycles. Chemistry driven biases. The specific chemistries of certain elements and molecules naturally favor the structures found in life. For example, the specific stability and properties of the RNA, sugar phosphate backbone, or the way amino acid link impose constraints that limit the sheer number of random possibilities, channeling the chemistry toward functional molecules. 3. Hypothetical pre-DNA protein scenarios. The Many scientists agree that the highly complex interconnected DNA RNA protein system could not have appeared all at once. Intermediate simpler systems likely paved the way. The RNA world hypothesis. This is the Lindy alternative to a simultaneous origin. It posits that the earliest life used ribonucleic acid (RNA) for both information storage (like DNA) and catalysis like proteins. RNA is simpler to synthesize than DNA and can fold into complex shapes with catalytic ability (ribozymes). This would reduce the required complexity for the first self-replicator, as one molecule could do the job of three: peptide nucleic acid (PNA) or treose nucleic acid (TNA) worlds. Other hypotheses suggest even simpler pre-RNA genetic polymers existed, which might be easier to synthesize under early Earth conditions, providing a stepping stone to the more complex RNA DNA. In summary, the apparent intelligent design is explained not by a sudden random event, but by a set of chemical and environmental filters (mineral scaffolds, wet-dry cycles, specific thermodynamics, and autocatalysis) that funnel the vast space of random chemistry into the narrow pathway that leads to the building blocks of life, making the outcome far more probable than a simple calculation of random chance would suggest. Now, but I I want to add that probably, or much sure, uh, humans uh, have a different concept of what is intelligence, such intelligence design, uh, visa that of nature. Probably nature have other other concepts at the base. What intelligent is meaning. Yes, and in final, uh, there remain a big gap of missing how such a big excessive amount of data of information, bringing into into work along with a lot of data processing in quite a short span time, which is 500,000,000 years when first cell appeared. Yes. Thank you very much. Bye bye.